Hello friends and welcome to Chemistry by AP. In today's video, we are going to discuss the spectroscopy in basics. So what is spectroscopy? It is a branch of science which deals with the study of an interaction of the matter with the light. That is the interaction of the electromagnetic radiation with a matter. So the electromagnetic radiation is composed of the two waves. That is the one is the electromagnetic field and one is the word electromagnetic itself implies that is the electric field and the magnetic field. So the electromagnetic radiation consists of the discrete package of an energy which are called as photons. These photons consist of an oscillating electrical field that is E and oscillating a magnetic field which is the both are perpendicular to the each other. Here is the source of the electromagnetic radiation. One is the magnetic field, one is the electrical field. Both are perpendicular to each other in the direction of propagation. So here are the basics of this wave. So the frequency of the wave denoted by the letter nu. It is defined as the number of a electrical field radiation oscillating in a 1 second. That is, from a given point, how much waves are passing in a 1 second. It have a unit of the frequency that is the hertz. Hz. 1 hertz is the 1 cycle per second. Next one is the wavelength denoted by letter lambda. It is the distance between two successive crests or the two successive troughs. So here is the distance which is the wavelength. So the relationship between this wavelength and the frequency can be written as C is equals to nu lambda. As photon is subjected to energy, so we can write E is equals to h nu, where nu can be written as C by lambda. So total overall equation becomes E is equals to hc by lambda. Here is electromagnetic spectrum of a light, which is consist of gamma rays, X-ray, UV, visible, IR, microwave, and radio wave. For energy, we can say the gamma rays having a highest energy, and with respect to wavelength, we can say that radio waves have a higher wavelength. If we are take a prism passing a white light, we are going to get a 7 colors of light with a different wavelength. For the violet light, we are going to have wavelength from 400 to 420 nanometers. For indigo, it is 420 to 440 nanometers. For blue, it is 440 to 490. For green, it is 490 to 570 nanometer. For yellow color, 570 to 585 nanometer. Then for orange, it is 585 to 620 nanometer. And at last, at the uppermost, that is the red, it is 620 to 780 nanometers. So here is the principle of the spectroscopy, on which principle the spectroscopy is work. The principle of the spectroscopy is very simple. So principle is based on the measurement of a spectrum of a sample consisting of atoms or a molecule present in our chemical compound. A spectrum is a graph which is the intensity of absorption or the emission of the radiation by a sample versus the frequency nu or the wavelength lambda. So spectrum is spectrometer is the instrument which gives the spectrum, that is the graph of an absorption or the emission of the radiation versus the frequency or wavelength. So as far as this spectroscopy is concerned, there are the two main types of the spectroscopy. One is the absorption and second one is the emission. An absorption spectroscopy is an analytical technique in which we are going to have the measurement of absorption of electromagnetic radiation. That is, our sample how much of the electromagnetic radiation will going to absorb by our sample. For example, in UV spectroscopy, absorption is from 185 to 400 nanometer. For visible, it is 400 to 800 nanometer. Similarly, in the IR spectra, it is 0.76 to 15 micrometers. In second, that is the emission spectroscopy, an analytical technique in which the emission, that is we are going to measure here the dispersion of an electromagnetic radiation. Example is the mass spectrometry. These are the three which are the energy level of a particular atom. That is, once the electromagnetic radiation which is absorbed by an atom, the atom can be excited. First one, which is the highest energy, is the electronic energy level. At a room temperature, the molecules are in the lowest energy level, that is the E0. When a molecule absorbs a UV visible light from an electromagnetic radiation, one of the outermost bond or the lone pair of the electron is promoted to the higher energy state like E1, E2 or to En, etc. are called as electronic transition. And the difference is delta E is equals to the h nu, where En minus E naught, where N stand, that is the 1, 2, 3 and onwards. Delta E for the electronical energy level is around 35 to 71 kilocalorie per mole. Second one is the vibrational energy level. These are the less energy level than the electronical energy levels. The spacing between the energy levels is relatively small compared to the electronical energy level, which is around 0.01 to 10 kilocalorie per mole. Example is the IR radiation is absorbed. A molecule are excited from one vibrational level to another vibrational level with a higher amplitude. And last one is the rotational energy level. These are the levels are to be quantized and discrete. These spacing between the energy levels of a rotational energy are even smaller than the vibrational energy level. It is often said that is the rotational spectra are the pure rotational spectra, but we can't get a pure vibrational spectra because a vibrational spectra is always associated with the rotational energy level, that is the rotational spectra. So the rotational energy, we are going to form a vibrational, and vibrational energy level gives formation of electronical energy levels. Energetically, we can say that delta E electronic is higher than the delta E vibrational than the delta E rotational. This is for this video. Keep watching, subscribe the channel and like this video. Thank you.